Hi, this is Professor Stugard, and in this video we're going to talk about how we can make language mathematical, which is really why ChatGPT works. So our goals for this video, first of all, we need to understand how we can represent words and their meanings in a mathematical way so that, obviously computers can do something with it. And then we're also going to just talk briefly about how applications like ChatGPT are really just these incredibly accurate prediction machines using neural networks to determine probabilities. So, the first thing though is we need to make our language mathematical. And that means we need to be able to turn words into some sort of mathematical object. And the main problem here is that we think of words based on their definitions, like from a dictionary. And how do we turn these dictionary definitions, though, into maths? Well, the way we're going to do that is using a vector because, well, vectors are useful for everything. But what we want to do is somehow take the meaning of our words and embed that into that mathematical structure of our vector. And in fact, embedding is that technical term that we use for trying to bring that meaning from the English language into our mathematical structure. Now, we're going to say that every word is a vector, but really it's every token is a vector, and a token could be a word or a punctuation, a prefix, a suffix. It's a little bit more complicated, but we can just think about it in terms of a word, and I think we'll be just fine. Now, to recap vectors, remember, conceptually, vectors are these mathematical structures that represent a direction in space and a size. Now, we usually visualize these with arrows because it just makes sense to have an arrow that's pointing somewhere in space that gives us a direction, and then depending on how long we make that arrow, that gives us our size. Now, computationally, the way we use vectors with any sort of computer science is that we consider vectors as a one-dimensional array of values. Or we can think about it as a matrix with just one column. Now, if we're trying to embed meaning into our words, we would conceptually expect similar words to point in similar directions. So, for example, let's say that I want to take the word cougar and embed cougar into a vector. Well, again, it's going to be some arrow in space that's pointing at a direction, and we would expect that similar words would point in similar directions. So, for example, puma would probably be pretty close to cougar because, again, puma, cougar, mountain lion, lynx, right? These are all large wild cats. We would expect them to be kind of similar, right? They have similar context and similar meaning. What's also really cool is that because of vector arithmetic, we can actually conceptualize the meaning that relates words together, or the relationship between words, or how these words are actually related to each other in the context of the English language. So, for example, let's say I have the words uncle and aunt, and again, they have been embedded into vectors. Well, if I want to look at the difference between these two, and so vector differences or vector subtraction is really how do I connect the tip of one to the tip of the other? And so direction matters. So in this case, I'm looking at how do I go from uncle to aunt? How do I go from those terminal points? Now remember, vectors in space have a direction, so they point in a certain direction, and a magnitude. They do not have a fixed position. They can be moved anywhere around in space. Now, typically standard position means we start those vectors at the origin, just like we did with uncle and aunt, but realistically, we can move them anywhere we want in the context of our problem. So if I have this vector that seems to represent how I move from uncle to aunt, well, really what that's doing is that represents a male to female association. How do I move from the male version to a female version of that same word? Because again, we want to embed not just the meaning of these words, but the context between them. We want to somehow figure out how these words are related to each other and make that a mathematical object. So once I have an idea for how I represent male to female association, I can do that for other examples. So for example, if I have the word prince, and I move that same direction, right? I take that same vector that represents a male to female association, we would expect that it would point at princess, because again, that's how we take prince and to make that masculine term into a feminine term, right? That direction that we move, we turn prince to princess, just like we turn uncle to aunt. Even though those vectors point in completely different directions, the difference between them, that green vector, is going to be the same. Now, this concept that we can look at how these vectors are different from each other, this vector subtraction, this can be applied to lots of different concepts, especially single to plural forms of words, right? Every time we make a word plural, we would expect a shift kind of in that same direction. We would expect that same change. But we can apply it to even larger concepts too, like the differences between countries and maybe their different leaders. So, for example, if I had some vector and I measured how do I go from America to George Washington, that distance from America to George Washington would be very, very similar if I took the vector from Germany to Otto von Bismarck, because those are both considered basically like the first leader of each of those respective countries. And again, the genius part is that, again, by representing words this way and representing their relationships this way, we can actually give context and meaning to words in the form of numerical vectors. Okay, now, admittedly, it's a little bit more complicated than what we just showed because I showed just a two-dimensional vector because we have a two-dimensional screen and we can see it very well. ChatGPT actually embeds every single word into a vector composed of 12,288 real number values. So what that really looks like is we take that word cougar, right, that word, we embed it into this matrix, and the matrix is going to have real number values. So real numbers means positives and negatives and decimals, and there's going to be 12,288 entries in that one vector. So basically, we need 12,288 different values to represent the word cougar and also its context in the meanings of all the other words and all the relationships between them. This is equivalent to thinking of vectors existing in 12,288 dimensional space. So, okay, we had vectors that were in two-dimensional space, and maybe you can imagine what a vector would look like in three-dimensional space, because now we just have arrows pointing in different directions in our normal space, but we can't really visualize 4 dimensions or 5 dimensions, let alone 12,288 different dimensions. We can't visualize it. Luckily, it doesn't matter if we can visualize it or not. The computers can still do math on it, and that means that we can still create our models even if we don't necessarily possess the ability to visualize what it looks like. But again, this also means that we have 12,288 different dimensions of freedom or ways to move. So again, in 3 dimensions, we have maybe left, right, forward, back, up, and down. Now we're talking about 12,000 different directions. So again, when we talk about the differences between words and that vector subtraction that gets us from one word to the other word and represents that relationship, that also can exist in this 12,000 dimensional space. So, yeah, it's a little bit more complicated than we can probably visualize in our heads. Luckily, it still works. Now, the ChatGPT dictionary consists of 50,257 words or tokens. And what we need to do is take all 50,257 of those words, we put them into a matrix where each individual word is a column with 12,288 rows, and this is called our embedding matrix. So our embedding matrix, which is W sub E, again, is this matrix where we have 50,000 columns, each with 12,000 rows, and that represents the initial ChatGPT dictionary that we start with. Anytime you type anything in, this is the first layer of the ChatGPT neural network. Just a quick thing about notations. Whenever we use that W, it means we're looking at a vector or a matrix composed of different weights. These are all weights that have to be trained. We don't know what those weights are. That's what the training portion of creating our model is. And then we have the sub E because it is our embedding matrix. That's how we keep track of which matrix is which. And again, lets us use kind of that really, really nice matrix multiplication notation to kind of encode meaning for us to learn from ourselves. Now, again, that means that that ChatGPT algorithm has to be trained for every single weight or every single value in that matrix. That means all 50,257 times 12,288 entries, which is a total of 617,558,016 different entries just in that one embedding matrix. So over 617 million just to find the initial weights or parameters for the ChatGPT model dictionary. But some words have multiple meanings. So consider the sentence, at the bar, a cougar bought a young man a drink. Now, in context, does cougar likely refer to a mountain lion or a puma? Well, I don't think so. I don't think a mountain lion is going to the bar to buy young men drinks. So what makes ChatGPT so effective is that it has the ability to consider the other words around it when determining what the word actually means. So I look at that word cougar, what ChatGPT is going to do is look at some of the words around it like bar, young man, drink, and it can actually take those words and update the meaning of the word cougar based upon the words around it. And this is how ChatGPT builds context for what we actually mean when we type in our inputs. But it's not just the word cougar. There's also the word bar, because bar can have multiple meanings as well. We have the bar, like a place you can go and buy drinks. We have a bar, like for construction. We have bar, like maybe a pull-up bar. We have bar, like the exam to get your degree in law. So which definition of bar do we mean? And again, ChatGPT looks at the context of all the other words around it, like bought and drink, and updates the meaning of the word bar. So even though we have our initial set of definitions, which is really just values in a matrix called our embedding matrix, ChatGPT is actually able to use the words around a certain word and update its meaning based on the context of the sentence. So this is ChatGPT transforming the meaning of a word based on the words around it. This is a process that is called attention and something that we might look at in a future video. But what's also great is ChatGPT keeps track of the order of the words in the input as well. And this is really important when we have adjectives that update the meanings of the nouns that come after it. So again, in English, if I had a noun like car, I would update the meaning of that word with adjectives before it. So if I said the fast red car, well, it's going to update what car actually means in the context of a fast red car. This also means that this requires many, many more layers to the ChatGPT neural network and a lot more matrix multiplication. Now, as we mentioned, that embedding matrix consists of over 617 million weights that need to be trained. That's our first step. That's our first input. We put our sentence into that embedding matrix, and then hopefully we gain some meaning, some first level meaning, I suppose, from what our input is. But then at the end of the process, what ChatGPT does is it has to unembed. So there is an unembedding matrix, which has the transposed dimensions, which means it now has 12,000 rows and 12,000 columns and 50,000 rows instead, which kind of reverses the process, and it outputs a single list, a single vector of our probabilities. What is the most probable next word in our sentence based upon all that data, all of that training that the ChatGPT model has gone through? In total, even though we have the 617 and the 617, so that gives us just over 1.2 billion, the ChatGPT algorithm actually requires over 175 billion weights to be trained, and the whole process is composed of almost 28,000 matrices and 28,000 instances of matrix multiplication. It is a very, very large model, but it's all mathematical, and it can all be understood by people. And it's really important to remember that all this ChatGPT model is doing is using all of this data that it's trained on. Basically, the entire internet was scraped. It was all put through this to find the weights that gives us our matrices that we're going to do a bunch of matrix multiplication. And at the end, it just gives us a probability function of what's the most probable next word. And then we pick one of the most probable next words. That's all ChatGPT is doing. It doesn't really know what it's doing. It doesn't have actual intelligence, as far as we understand intelligence at least. It's just making a prediction for the next word, and it's just really, really good at that. Now, one of the big breakthroughs, the reason ChatGPT works so much better than everything else, is not only its ability to consider the context of the input, but it has the ability to consider thousands of surrounding words as contexts. So again, we looked at one sentence where we had a couple words that seem to influence what the meaning should be, which again changes where that vector points in space. It actually can consider the thousands of surrounding words. It can consider a huge amount of input, and it updates the definitions of every single word in the input based upon the definitions and contexts of every other word and its positioning in each sentence. That's pretty incredible, but at the end of the day, it's just matrix multiplication. It's just a neural network, and all it is doing is predicting which word should come next based on those probabilities. Kind of think like the auto-completion feature that we see now in our text messaging or sometimes our emails. It's thinking, well, what's the next most likely word? And it is very, very good at that. It has been trained very well. Now, that's all we're going to cover in this particular video. So can you answer the following questions? First of all, what is a vector conceptually and computationally? And then, again, I want you to just really think and consider how many dimensions are actually required for us to embed the meaning of words in a mathematical sense. What dimensional space do we use? All right. Well, I hope this was kind of interesting. I hope you learned something. And as always, please take care of yourselves.